Welcome to this presentation on an introduction to cryptography. Let's begin by defining what cryptography is. Cryptography is the process of converting information or data into code, especially to prevent unauthorized disclosure. There are a number of cryptography methods including steganography, symmetric cryptography, which includes the following cipher types: Caesar cipher, substitution cipher, data encryption standard, and the advanced encryption standard. Then there is asymmetric cryptography, which is often referred to as public key cryptography. All of these cryptography methods will now be described in more detail. Steganography is the practice of concealing messages or information within other non-secret text or data. This is different to cryptography, as cryptography is the practice of protecting the contents of a message alone. Steganography is concerned with concealing the fact that a secret message is being sent, as well as concealing the contents of the message itself. In the film Beautiful Mind, John Nash was convinced that a message was hidden in the linkages between newspaper and magazine articles. If this was true, then this would be an example of steganography. Another example of this could be the Babington plot, where a message was concealed within a barrel bung. However, some could argue that this isn't really steganography. Another example could be where a message is tattooed on someone's head, and then concealed by hair growth. Amazing as it may seem, but this really did happen. Another example is where messages were written on boiled eggs, using shell-penetrating ink. A modern-day implementation of steganography is where every nth letter of a message is embedded within an image file. Now, let's look at some methods of symmetric cryptography. Symmetric cryptography is where a message is both encrypted and decrypted with a single key. One of the first ciphers to use symmetric cryptography was the Caesar cipher, that Julius Caesar used to communicate in secret. The Caesar cipher's encryption algorithm is based on shifting a character, either left or right in the alphabet, by a number of places. The actual secret, or the key, is the number of shifts that a letter is to be moved up or down the alphabet. The key space of the Caesar cipher, which is the number of different key combinations, is 26. However, for Caesar, it was only 23. In its day, the Caesar cipher would have been considered secure, because those handling the enciphered text were generally illiterate. However, being secure in today's world is a lot more than just encrypting text. Another common symmetric cipher is the substitution cipher, where one letter is always substituted with another fixed letter. The key space, or the number of different key combinations, for the substitution cipher, is 26 factorial, which is 4 times 10 to the power of 26, which is a very big number. To get an idea of just how big 26 factorial is, consider that there are approximately 10 sextillion stars in the universe. That's 10 to the power of 22 stars, and 26 factorial is about 40,000 times larger than that. Today, the substitution cipher is considered insecure, which is somewhat counterintuitive, considering that it has such a gigantic key space. Another symmetric cipher is the data encryption standard. The data encryption standard is what is known as a block cipher, based on a 56-bit key. It was developed by IBM in the 1970s, and has 2 to the power of 56 key combinations. The data encryption standard was approved as a federal standard on the 15th of January 1977, and was known as FIPS Publication 46. The data encryption standard was predicted to have a 15-year lifespan, but in reality, it only lasted for 11 years. It should be noted that the data encryption standard has a considerably smaller key space than the substitution cipher, but counterintuitively, it was vastly more secure. As computers got faster, they were able to brute force search a key space in an ever-decreasing amount of time. Governments realized that, taking into account Moore's law, time was up on the data encryption standard, and something had to be done. So, in 1998, the National Institute for Standards and Technology, known as NIST, issued a call to the cryptographic community to submit proposals for a new encryption standard, to replace the data encryption standard. The winning proposal, which was the Rindale cipher, became to be known as the Advanced Encryption Standard, and was approved as the Federal Encryption Standard, published in 2001, as FIPS Publication 197. The key space of the Advanced Encryption Standard is 2 to the power of 256. The governments of 1998 were right to be concerned, as by 2007, it was shown that the data encryption standard could be cracked by a computer costing just $10,000 in just 6.4 days. Symmetric encryption has a problem. The most fundamental problem associated with symmetric encryption is that both parties must have knowledge of the same key. So, somehow the shared secret key has to be distributed to all parties in a secure manner. This is known as the key distribution problem. The number of keys required is n times n minus 1 divided by 2, where n equals the number of parties. Thus, when 10 parties wish to communicate in secret, then the number of symmetric keys that would have to be distributed amongst the group would be 45. Even with a secure symmetric encryption algorithm, the keys have to be distributed, and how to do that securely was thought to be an unsolvable problem for centuries. Some methods of key distribution are as follows. Person-to-person key exchange, which is expensive and time-consuming, especially over large distances. The use of a messenger. Out-of-band key exchange, using the telephone or the postal service. Secure courier. Steganography. Diplomatic bags and channels. Birds, as used in Game of Thrones, Harry Potter, and both World Wars. All of the above methods of key distribution rely on trusting a third party, person or bird, and trust can never be guaranteed. In order to solve the key distribution problem, public key cryptography was developed, and has the following benefits. There is no need to share a common key. There is no need to meet with a third party in order to distribute a secret key. Public key cryptography provides message integrity, origin authentication, and non-repudiation. However, public key cryptography does have some issues, which include: third parties are now basing their trust on certificate authorities. The problem shifts from maintaining secrecy to one of key management. Certificates have a lifespan and may become out of date. The main threat to the integrity of public key cryptography is that quantum computers may be able to break the public key encryption algorithm within a short amount of time. Well, that concludes this brief presentation on cryptography. I hope you found it useful, and don't forget to check out the other information security tutorials available. And thank you for watching.